Hello, welcome. In this video, you will take your first steps in reinforcement learning. We'll train a Q-learning agent from scratch. Not only that, you will also build the environment that the Q-learning agent will be trained on. This is a very important video if you want to learn reinforcement learning. This is the foundation of many modern and advanced reinforcement learning algorithms. If you get the concepts here, they will help you a lot in the future algorithms. In Q-learning, we create a Q table from all the possible states and actions. We then learn good actions to take in each state by iteratively interacting with the environment and update the Q table accordingly. It does not require us to know the transition probabilities, so this algorithm is model-free. Good state action pairs get assigned higher Q values in the Q table. Once the Q-learning reaches convergence and the Q table stops updating, we can extract the optimal policy. This is done by selecting the action that yields the highest Q value for each specific state. Let's have a look at the tabular Q-learning update step and then start coding everything from scratch in Python. Tabular Q-learning update, we continuously use this update step until we have reached convergence and then find the optimal policy. So we make the update based on the current Q value for a state action pair and the target. The weight we give to the current Q value and the target is based on the learning rate, which is the hyperparameter in the Q-learning process. Target is based on the reward for the transition and discounted future Q value. If we are in a terminal state, the reward for going into the next state is the target. If you want to understand this in detail, please check out our previous video and lesson. Now let's start coding. I'm assuming that here you are already comfortable with Python, as our entire focus will be on the Q-learning process itself. I'm excited as this is the beginning of a very interesting learning journey, pun intended. I have opened the code in the Jupyter notebook here, and you can find out complete code on our GitHub. Link is in the description. The first thing we need to do is make all the necessary imports here. We'll use random for random number generation, as we'll need it for our epsilon greedy strategy that we'll implement. We'll use NumPy to build our Q-learning agent. We'll use matplotlib for plotting. And to make it a bit more beautiful, we'll use listed color map. We'll also seed random and NumPy modules so that what I do here is reproducible when you use the notebook on your own. To keep it simple, we'll create a simple 2x3 grid world and solve it. This is how the grid world would look like. There are 6 possible states. The state 02 is the goal state with a reward of +1, and state 12 is the obstacle state with a reward of -1. All other states, as you can see, have a reward of 0. From each state, we can take 4 actions. We can take up, down, left, and right. All of this is part of the environment. The agent has to figure out all this out. It only knows which actions it can take and not about the rewards or penalties. So we'll create a class called gridworld 2x3. We define that this world or this environment has 2 rows and 3 columns. We define the goal and the obstacle state. The goal state is the 02 state and the obstacle state is the 01 state. We also define a starting state, as we'll be resetting this environment after each episode. You can consider an episode to be like one try at playing the game. The episode is over when we either win or lose the game. So when we either reach the goal state or we are in the obstacle state, the game is over. Then here in the init function, we initialize a grid world of size rows and columns, which is 2x3. We set a reward of +1 for the goal state and a reward of -1 for the obstacle state. We also initialize the state of the world to be the starting state, which is 01 in this case. We also need to have a reset function in this class that we'll use at the start of each episode so that we can reset the environment and start from the starting state, which is 01. So this is the reset function. It just sets the state of the system to the start, which we have defined right here. We also need to have a isTerminal function to check if the current state that the environment is in is a terminal state, as we need this information for target calculation. Then we have a step function, which is the function that will be used at every step of the learning process. This function helps us take the action and reach the next state if the action leads to a new state. During the training process, when we use this function, it will return the state that resulted from that action, the reward for taking that action, and whether the state we transitioned into is a terminal state or not. This is what we need for the Q-learning training process. Inside this function, you can see as the agent will decide which action to take, this step function will try to take that action. We get the current state of the environment. Based on the action, we change the state if it's possible. So if we take an action up, if the action is 0, that means we want to go up. We'll check if that's possible. Similarly for right, left, up and down. So for all of them, we'll check if that action is possible. If that action results into a new state, like right here, if we are in this state and we take right, it can result into a new state. But if that action doesn't do anything, for example, if in this state you take up or left, you will still be in the same state. If the action results in a new state, we update the current state of the environment. We get the reward for being in that new state, and we also check if it's a terminal state. Then we return all this information for the agent to learn. Now let's create our Q-learning agent class. We'll call it Q-learning agent. At top, we define 4 actions we can take: up, right, down, and left. These are just for readability. They don't affect the logic. Now in the init function, we define everything we need to set up our agent. We first create our Q table. It has the same shape as the grid world, but with 4 values for each state, 1 for each action. So for every state, we store the value of taking each possible action from that state. Then we store our learning rate, discount factor, and epsilon for exploration. These are the core hyperparameters for Q-learning. Now we define the function to choose an action. This uses epsilon greedy strategy, which means sometimes we explore and sometimes we exploit. If the random number is less than epsilon, we take a random action. Otherwise, we pick the best action we know so far for that state, the one with the highest Q value. Now comes the heart of Q-learning, the update rule. This is where we actually learn. We follow the tabular Q-learning formula. For the update rule, we have the information about the state, the action the agent chose to take from that state, the reward for taking that action, the resulting state, and if the next state was a terminal state or not. Based on this, we update the Q table. We get the current Q value. If the next state is a terminal state, the target is just the reward. But if it's not, otherwise we take the max Q value from the next state and use that to compute target. Then we update the Q value for that state and action we just took. This is the full Q-learning update in action. We also have a print Q table utility function right here. You don't need to fully understand this. This is just to visualize the Q table in a nice way. Also, there are some additional helper functions in the notebook. Don't worry about these other functions or helpers. The most important goal for you is to understand Q-learning algorithm. The rest of it is just for visualization. Now that all our components are built, we can start training the Q-learning agent. The first step is to initialize the environment and the Q-learning agent. As a part of this initialization, we also set the hyperparameters, which are learning rate, exploration rate, and discount factor. I will also print the grid and also plot it right here so that you can see how it looks. So this is how it looks. You can see the rewards here. For these 4 states, the reward is 0, and for the goal state, it is 1, and for obstacle state, it is -1. There is also this visualization right here, which is nice. Now let's take a look at the training loop. We'll train the agent for 500 episodes. Then we loop through each episode. At the beginning of each episode, we reset the environment so that agent starts fresh. Then, while the episode is still running, we do the following. The agent chooses an action based on the epsilon greedy strategy that we just defined. We then take the action in the environment using the step function that we defined. From there, we get the information about the next state, the reward, and if it's a terminal state. Then we update the Q table in the agent based on this information, based on the state we were in, the action we took, the reward we got, the next resulting state, and if it was a terminal state. And we move the agent to the next state. Once the episode is done, we print the Q table so that we can see how it's changing after each episode. Let me do this. This helps us track the learning process step by step. When I run this, you will see initially everything starts 0, nothing. And after 500 episodes, you can see right here, I will scroll down to the bottom After 500 episodes, you will see how the queue table looks like. After 500 episodes, we see that the agent has converged. Queue learning table has not been updated since episode 391. We can extract the optimal policy now. To extract the optimal policy, we need to pick a state action pair with a maximum queue value. This means after training or convergence, when the agent is performing its task, it always picks actions greedily as we want only the best actions to take. We are not experimenting anymore. So when I run this, you can see from each state, it is telling us the best action that it will take. From here, it makes sense to take right. From this one, also right, which will take us closer to goal. Similarly, from this state, it will take an action up. And from this state, it decides to take an action up. You can also see this representation from the queue table right here. Congratulations! You have now trained your first reinforcement learning algorithm from scratch. You created an environment and the agent. Then you use the queue learning agent to solve the environment. That is awesome. There is still something I want to talk about in detail, the hyperparameters. I have done this as part of the written lesson. If you are curious, please check that out. Link is in the description. But I think it makes sense to talk about the effect of these hyperparameters in a more complex environment. This is just the beginning. We'll soon start working with algorithms that are capable of doing much more complex tasks. And we'll train these algorithms to land a lunar lander reliably and effectively. Next, we'll introduce the lunar lander environment in detail before going into deep reinforcement learning.
To find the entire detailed lesson with all the instructions, math and code, visit our website edreate.com. There you can find everything you see here and much more. Plus, you can find the full code on github.com/edreate. So don't wait around and sign up now at edreate.com.